Hello and welcome to this revision session for Combined Science and Physics for GCSE Paper 2. So in today's revision session what we're going to do is see if we can answer examination questions on the GCSE Physics Paper 2 part of the GCSE Combined Science. So if we are successful and learn in this revision session, we should be able to answer GCSE Combined Science Physics examination style questions. You should be able to assess your understanding on the GCSE Combined Science Physics course, and then finally understand what topics you need to improve on for the GCSE Combined Science Physics course. So how should you carry out this revision session? Well, when completing your work in this revision session, divide your piece of paper into two sections. Make the section on the left hand side larger than the right hand side, and in this left hand side section write down your working out and answers to the questions in the revision session. And then when you do this, make sure you write your answers in full sentences and show the full working out. Whilst in the right hand side in this section, write down any pieces of information which you find useful or any hints and tips on answering questions from this revision session. And at the end of the revision session, write up these notes into a revision sheet for you to use independently. So let's have a look at a few questions from the GCSE Combined Science Physics Paper 2 section. So the first topic we're going to look at is forces. So let's look at the following question. The student increased the resultant force acting on the glider by adding more masses to the mass holder. She calculated the acceleration of the glider for each resultant force. Each test was done 3 times and table 1 shows the results. The student made 2 mistakes in the mean acceleration column. Identify the mistakes the student made and suggest how each mistake can be corrected. So pause the video now, then unpause the video when you want to go through your answer. Right, so when you look at this question, there's a few things that stands out to you. Firstly, you're going to have to look at the calculation of mean acceleration from the 3 tests, and secondly, you should look to the number of decimal places / significant figures in each column. So the first mistake you can see is that in the calculation for the mean acceleration when the resultant force is 0.20 has a lot of decimal places or significant figures, much more than the other rows. So for example, 2.6, 3.8, 5.1, 6.7 all have values to 1 decimal place, whilst 1.26667 is given a value to 5 decimal places. So the first issue you're going to have is that value in the 0.20 row is in fact written to the wrong number of decimal places, or you could say significant figures. So you would give your value to 2 significant figures or 1 decimal place like all the other values in that column. Whilst the second issue is when you are calculating your mean. Now if you look at the mean acceleration for 0.98, you can see that what you've got is an anomalous result. You know this is anomalous because one of the results will be much different compared to the others, but it should be discarded from the calculations of the mean and not included. But you can see from that value of 0.98 across is 6.7 that they've included that anomalous result in the mean calculations. It's always important that you check that in any results table that the number of decimal places / significant figures is consistent in each column, and then secondly that any anomalous results are discarded and are not used when you recalculate the mean. Let's look at the next question. Figure 1 shows a cyclist with a trailer attached to his bike. Describe how Newton's third law applies to the forces between the bike and the trailer. A student investigated how the stop and distance of the bike was affected by the mass of the load. The same person rode the same bike throughout the investigation. Give 2 other variables which the student should have controlled. So pause the video now, then unpause the video when you want to go through your answer. Right, so the first thing is you've got to explain Newton's third law. Now Newton's third law is that when you have 2 objects, now in this case it's the load and the cyclist, when you have 2 objects, they will exert equal yet opposite forces of the same type on each other. So you can say that in this instance, and you've got to actually link it to the situation given in the question, the forces of the bike on the trailer and the trailer on the bike are equal in size. yet are opposite in direction, and it's the same type of force. So the force of tension from the bike to the trailer and the force of tension from the trailer to the bike. Now, a student investigated how the stopping distance was affected by the mass load. So what other variables should you have controlled, i.e. what other factors in the investigation could make a difference to the actual stopping distance of the bike apart from the mass of the load. So think about what has to be kept the same so it doesn't also affect the results. So it could be the same trailer should be used, the weather conditions should be the same road surface should be used, the same gradient of the road should be used, the same speed should be used, and the cyclist should have the same level of alertness throughout the experiment. Let's look at the next question. A student investigated acceleration using gliders, an air track and light gates. The air track reduces friction between the glider and the track to zero. The glider was released from rest and moved along the track. The mass holder hit the ground before the card passed through the second gate. Which two statements describe the effect this would have on the glider? So pause the video now, then unpause the video when you want to go through your answers. Right, so you've got to think to yourself, what would happen in this particular situation? So if we carry this out, the mass holder hits the ground before the card passes through the second light gate. Well, the mass is providing the resultant force through its weight to accelerate the actual card along the surface, because we know F equals ma. So if you have a resultant force, in this case due to that mass, you will get an acceleration. So if that mass holder hits the ground, there's no longer a force pulling the actual glider and cart downwards, so that resultant force has decreased, so therefore the acceleration would decrease to zero, because that resultant force downwards has decreased to zero. And there are your two options. Next question. The glider was released from rest and moved along the track, and like mentioned before, the mass holder hit the ground before the card passed through the second light gate. The mass holder should not hit the ground before the card passes through the second light gate. Suggests one way that the student could stop this happening. So pause the video now, then unpause the video when you want to go through the answers. Now again, you've got to have a good understanding of the experiments that are part of the required practicals of this course, but also in addition to that, you've got to use the information given in the question. So look at the labelled apparatus you've been given in this question and look to see how you can adjust it so therefore the mass holder does not hit the ground before the glider has passed through that second light gate. So the obvious one is to move the second light gate closer to the first, because there's less distance for it to travel, so therefore I'll get to it faster. Or you could make the string length shorter, so therefore it's very unlikely that the mass holder will hit the ground first. Next question. A student investigated the motion of a glider on an air track. Figure 6 shows this apparatus. The speed of the glider is the same at both ends of the air track. What is the tendency for objects to continue at the same speed in the same direction called? And the glider has a mass of 0.14 kilograms and a velocity of 17 centimeters per second. Calculate the momentum of the glider. So pause the video now, then unpause the video when you want to go through the answer. So this first question is just a key fact, a key bit of learning, a key definition in physics. So we call the tendency for an object to continue at the same speed in the same direction if no resultant force acts on it. We call that idea inertia, and it was devised by Sir Isaac Newton. Now the next question is calculate the momentum of the glider. Now there are a couple of steps to this particular question. The first one is you've got to remember and recall the equation for momentum. Now the equation for momentum is mass times by velocity, so P is equal to mv. The next thing is you look at the units of the question. Now we normally work with mass in kilograms, so that's fine, so 0.14 can be used in your calculation, but we don't work in centimeters per second, we work in meters per second. So the first job you've got to do is convert centimeters per second into meters per second. So momentum is equal to mass times by velocity, then place the values into the equation, so it's 0.14 times by 0.17, so the answer is 0.024 kilogram meters per second. Next question. Figure 5 shows an ice skater, skater A. Write down the equation that links mass, momentum and velocity. Then skater A travels with a velocity of 3.2 meters per second and has a momentum of 200 kilograms meters per second. Calculate the mass of skater A. So pause the video now, then unpause the video when you want to go through your answer. Right, so the first thing you've got to do is recall the equation for momentum. Now, like mentioned before, you've just got to memorize it. You've just got to state it. So that is, momentum is equal to mass times by velocity, or P is equal to mv. And those are our symbols of the different quantities, where P is momentum, m is mass, and v is velocity. Now, if you're doing a higher tier paper in GCSE Combined Science Physics, it's very unlikely that you'll just be asked to work out a value just from the simple equation. They'll probably ask you to rearrange it. So what we can do for this question is we can say that 200, which is the momentum, is equal to mass times by 3.2. Now, you'll notice in this format, AQA suggests the best way to answer these questions is to place the numbers in first, then rearrange. So we say 200 is equal to m times by 3.2. So m is equal to 200 over 3.2. It's over 3.2 because on the other side of the equals, it's a times. So when you go from one side of the equals to the other side, a times will become a divide and vice versa. So it's 200 over 3.2, so you get 62.5, which rounds to 63 kilograms. And again, the best people in physics would then look at the answer and say, does that look right? So what you would then do is you just say, does it look right for 63 kilograms to be the mass of an ice skater? And it probably is, so it's most likely to be right. Let's look at the next question. Skater A bumps into another skater, skater B. Skater B is stationary. The skaters move off together in a straight line. Explain what happens to the velocity of each of the skaters. Use the idea of the conservation of momentum. So pause the video now, then unpause the video when you want to go through your answer. Now, the most common mistake people make in answering this question is they answer the question in terms of forces or in terms of energy. So you could talk it about in terms of kinetic energy. Now, it's best not to do this in this question because it literally says in the question, use the conservation of momentum. Now, if it says to you in a question, use the conservation of momentum, you obviously have to use it, but first, you've got to define it. So the definition of the conservation of momentum is that the total momentum before a collision is equal to the total momentum after a collision. Now you'll notice that before the collision, A is moving and B is stationary. Now we know momentum is mass times by velocity, so therefore if skater B has a velocity of 0, it is stationary, it must have a momentum of 0. So therefore B has a momentum of 0 and A has a value of momentum. We know this because the skater will have a mass and they're also moving, so they have a velocity. Now when they hit together, we know that the total momentum before has to equal the total momentum after. So therefore, the momentum of skater A before the collision is bigger than the momentum afterwards because it's got to give some of its momentum to skater B so that can now move. So as a result, the momentum of skater A decreases, but now the momentum of skater B increases because the total momentum is being shared between skater A and skater B after the collision. Now therefore that means if the momentum of A is going down and momentum is mass times by velocity and the mass of the skater isn't changing, the velocity of A goes down, whilst by the other token, the velocity of B goes up. Next question. Some quantities are scalars and some are vectors. Which of the following quantities are scalars? Then give the difference between a vector quantity and a scalar quantity. So pause the video now, then unpause the video when you want to go through your answers. Right, now it's very important you can do two things. You can define scalars and vectors, and you can also identify scalars and vectors. So in this instance, displacement is a vector, distance is a scalar. It's actually the scalar equivalent to the vector of displacement. You've got force, which is a vector, speed, which is a scalar, and velocity, which is a vector. Now again, speed is the scalar equivalent of the velocity vector. So the answers are distance and speed. Now this difference between the definition between a scalar and a vector is linked to the definition. So a scalar is a quantity with only a magnitude, a number, whilst a vector has this number, has a magnitude, but it also has a direction. So the definition or the difference between the two is that vectors also contain a direction term, but while scalars don't, but they both have a magnitude. Next question. Bumper cars are a fairground ride and are designed to bump into each other. Figure 5 shows two bumper cars moving towards each other. The momentum of each bumper car is shown by an arrow. Give two factors that affect the momentum of each bumper car, then the bumper car crash into each other and stop. Explain why both cars stop after the crash. So pause the video now, then unpause the video when you want to go through the answers. Right, so let's think of factors that can affect momentum. Now, the ideal answer is thinking about the factors in the equation. So we know momentum is equal to mass times by the velocity. So the mass of the car and the velocity of the car are valid answers. But you can also think about this particular situation. Well, the friction that the bumper cars generate will affect the momentum because that affects the velocity. And so does the power of the motor. Because the more powerful the motor, the faster the bumper car can travel, so the higher the velocity. Now the two bumper cars crash into each other and then stop. So what's going on? Well, if you've got a collision or a crash, it's most likely going to be the conservation of momentum. So we know that after the collision, the total momentum is going to be zero. We know this because both cars have stopped. So when your velocity is zero, when you are stationary, your momentum must be zero. Now that tells us that beforehand, if the conservation of momentum is true, that if it was zero afterwards, it's got to be zero before. Now how can you have two cars moving yet create a zero momentum in total? It's because direction is signified in physics with a plus or a minus. So because one is a plus value and one is a minus value, that they will have equal yet opposite answers, so as a result they'll equal out to zero. So the total momentum of the bumper cars was zero before the collision because there's a positive momentum on one hand and a negative momentum on the other, so they cancel out to be zero, so therefore the momentum will be conserved. Next question. There is a resultant force on a paperclip. The resultant force causes the paperclip to accelerate towards the magnet. Write down the equation that links acceleration, mass and resultant force. The mass of a paperclip is 0.012 kilograms. Calculate the acceleration of the paperclip when the resultant force on it is 0.000168 newtons and give the unit. So pause the video now, then unpause the video when you want to go through the answers. So once again, what do you have to do? So you have to you've got to remember your equations. So you've got to know that force is equal to mass times by acceleration. F is equal to ma. So that's an equation you've just got to memorize. Now this next one, again, you need to work out acceleration. So the first thing you would need to do is pop your values into the equation. So we know that force is equal to mass times by acceleration, a very important equation you've got to remember. So we can therefore say 0.00168 is equal to 0.0012 times by a. You can then rearrange and say a is equal to 0.000168 divided by 0.0012. Again, if it's times on one side of the equation, it's divided on the other. And therefore the answer is 0.14 meters per second squared. Now again, when we're doing our calculation, we double check to see that there are no prefixes in our units or the wrong units, so like seconds or hours when it should, so hours or minutes when it should be seconds, or for example kilonewtons when it should be newtons. So you always check your values to make sure that you've got the right units, and then you should always state the unit at the end of the calculation. So it's 0.14 meters per second squared. Let's have a look at the next question. The conservation of momentum can be used to understand what happens during collisions. Momentum is a vector quantity. Explain the difference between a vector quantity and a scalar quantity. Then describe what is meant by the conservation of momentum. So pause the video now, then unpause the video when you want to go through your answers. So, how do you answer this first question? Well, again, it's about defining vectors and scalars. So what's the definition of a vector? What's the definition of a scalar? These are definitions you've just got to know. So vectors have a magnitude or a size and a direction, but scalars only have a magnitude. Now again, what is meant by the conservation of momentum? So the first thing to note is in the conservation of momentum, the total momentum before is equal to the total momentum after a collision. So before the collision, the total momentum of all the objects involved is equal to the total momentum of all the objects involved after the collision. Well, this is only true in a closed system where no outside forces act on the objects, which is an important caveat to remember when you're doing this definition. Let's now have a look at the topic of waves. So the first question is describe how the radio waves reaching the car aerial produce signals in the electrical circuit of the car radio. So pause the video now, then unpause the video when you want to go through your answers. So it's very important that you understand how a car aerial will produce signals in the electrical circuit of a car radio. So you've got to know the link between what happens with aerials and receivers and also the radio waves. So the first thing to note is the car aerial will absorb radio waves or energy. Now that makes the electrons in the metal vibrate. Now if electrons are all oscillating or vibrating backwards and forwards, we call that an alternating current. So the absorption of a radio wave by an aerial will cause an alternating current to be produced in the actual aerial. Now the last thing to always remember is that the frequency of the alternating current is the same as the frequency of the radio wave. Next question. There are different types of electromagnetic waves. Firstly, what type of electromagnetic wave has the shortest wavelength? Then secondly, a new technology has been developed to charge small electrical devices from the radio waves in the air around us. Explain how radio waves could charge a small electrical device. So pause the video now, then unpause the video when you want to go through your answers. Right, so the first thing you've got to know is you've got to know the basic properties of all the different parts of the electromagnetic spectrum. So the shortest electromagnetic wave is a fact, you've got to learn it, it's a gamma wave. Now how I remember it is the shorter the wavelength of the electromagnetic wave, the more dangerous and more ionizing the wave is. So gamma is the most ionizing wave, so therefore it has the shortest wavelength and the highest frequency. Now the next one is talking about radio waves. Now again, you've got to remember the link between radio waves and alternating current. Now if you had an alternating current, that can then charge up an electrical device. So you'd say that device absorbs the radio waves, and that will cause the electrons in the device to oscillate backwards and forwards, so it will produce an alternating current. And again, what's the important part? It's at the same frequency as the alternating current, or has the same frequency as the radio wave does. Let's now have a look at the topic of magnetism and electromagnetism. So let's have a look at the following question. A magnet produces a magnetic field. Which diagram shows the magnetic field pattern around a bar magnet? Then figure 3 shows 3 metal blocks. The blocks are not labelled. One block is a permanent magnet, one block is iron, one block is aluminium. Describe how another permanent magnet can be used to identify the blocks. So pause the video now, then unpause the video when you want to go through your answers. Right, so the first thing is you've just got to be able to recognise the magnetic field pattern around a bar magnet. Now the first thing to note is it looks like either the top left or the top right, because you've got lines not going around as a full circular track, but you've got some lines going from north to south. Now you'll notice there's a slight difference between the top left and the top right because the arrows are going in opposite directions. Now how you always remember it is that in this particular instance it's the first box ticked because the field lines will always go, the arrows will always point in the direction from north to south. So that's because the field line, the arrows point in the direction a positive charge would take. So they go against the North Pole because they would repel it. It would go towards the South Pole because it would be attracted. The next one again is a very important question type because it's asking how you can identify different materials using a permanent magnet. Now the important thing to note is firstly you've got to identify what things are magnetic materials and what are not. Now iron is a magnetic material whilst aluminium is not a magnetic material. So what you would say is aluminium would have no effect from the permanent magnet because it's not a magnetic material. Now the next idea is very key and very crucial, that magnetic materials such as iron can only ever be attracted to a magnet. Now the only thing that can be repelled by a permanent magnet or be repelled by a permanent magnet is another permanent magnet. So sometimes, depending on the way you've got the permanent magnet turned around, it will be attracted to the permanent magnet, but other times it will be repelled. But the important thing to note is a magnetic material, no matter what direction it's pointed in, no matter what side of it is being shown to the permanent magnet, is always attracted. The only one with the ability to have repulsion is the permanent magnet, which allows you to tell the difference between them. Let's have a look at the next question. Figure 3 shows a bar magnet. Complete the diagram to show the magnetic field lines around the bar magnet. Then describe a method using a compass to plot the magnetic field lines around a bar magnet. So pause the video now, then unpause the video when you want to go through your answers. Now again, it's very important you can recognize and draw a magnetic field lines, the magnetic field line pattern around a bar magnet. So again, it's the particular image shown here. So you've got your semicircular lines going out of north to south, and then your straighter lines coming out the pole of north going towards south. It's very important you can memorize the actual magnetic field line pattern of a permanent magnet. Now the second thing is showing the direction of the arrow. The direction of a field line is just as important as the actual pattern it produces. So you've got to show that arrow giving the direction of the field line. And like we said before, magnetic field lines always point from north to south. So that's because it goes in the direction that a positive charge would take, and a positive charge would be repelled by north but attracted to south. So you see that particular image. Now the next one again is describe a method using a compass to plot magnetic field lines around a bar magnet. So you've got to know this methodology. So you would place the magnet around a piece of paper, draw around the magnet marking north and south, place the compass by a pole of the magnet either north or south, make a dot at the tip of the compass needle, move the compass needle to the new dot, make a dot at the tip, repeat until it reaches the other pole of the magnet, and then draw a line in there to show the direction of the magnetic field line. So that's very, very important, and you don't just do it for one particular field line, you do it for a number, at least 6 or 7. Again, it's very important you know how to do these different practicals. Let's have a look at another question. Explain why a compass needle moves when placed near a bar magnet, and then finally, iron is a magnetic material. Which of the following is also a magnetic element? So pause the video now, then unpause the video when you want to go through your answer. Now again, you've got to understand how compass needles work. Now if you think about it, a compass needle can be moved to any position. It can be attracted or repelled. So the only thing that can be attracted or repelled when it's next to a bar magnet is another bar magnet, which tells us what a compass needle truly is. So a compass needle is a small bar magnet, and therefore the compass needle and the other bar magnet will exert a force on each other, cause an attraction or repulsion, which will cause the needle to move. Now the next question is state which of these is the magnetic element. So as a result, you've got to work out which one it will be. Now you've just got to know these as a fact, that it would be cobalt. Now the other thing is that it's put in bold element, because they're trying to trick you here, because steel, whilst it is magnetic because it has iron in it, because steel is an alloy, not an element. So therefore you've got to be very careful when reading the question. So that brings us to the end of this revision session. So if you've been successful and learnt in this revision session, you should be able to answer GCSE Combined Science Physics examination style questions, assess your understanding on GCSE Combined Science Physics, and then finally understand what topics you need to improve upon for GCSE Combined Science Physics Paper 2. So thank you very much for watching this revision session, and as always, have a lovely day.